James Webb is taking us on a journey into the unknown, as its razor-sharp eyes focused on distant and primordial parts of the cosmos. The telescope captured something perplexing near the beginning of time that made astronomers' jaws hit the floor. They shouldn't exist, but apparently do. Monsters lurking in Webb's images then prompt a rethink of our understanding of cosmic history. Join us as we dig deep into how James Webb reveals a universe that even scientists find overwhelming. To start, it's helpful to recall what James Webb was built for. On Earth, astronomers often build telescopes on mountaintops and in remote deserts for an unobstructed view of the sky. But the Earth's atmosphere still mars the view. Space is the ultimate mountaintop, as NASA explains. James Webb launched in December 2021 as the successor to the Hubble Space Telescope, and it improves on its predecessor in several ways. For instance, because of its huge golden mirrors and infrared cameras, it can make better observations of planets orbiting stars other than our Sun. But for this discussion, what matters is how it can observe farther back in time than the Hubble telescope. In astronomy, the farther away an object is in a telescope's mirror, the older it is, because light needs time to traverse such large distances. Some of the light James Webb captures is almost as old as the universe itself, dating back to 100 million to 250 million years after the Big Bang, the relatively infant days of our universe, which is believed to be 13.77 billion years old. That light is so far away, it has been traveling nearly the age of the universe to reach us. So, when the Webb focuses its mirrors on a particular patch of sky, it can see through time. The farthest objects in the image are the oldest. Those in the foreground are more current. The images that contain this rich history are called deep field observations. And while they appear in two dimensions to us, in them, scientists can see how the universe has evolved. Before James Webb, the Hubble Space Telescope gave humanity its deepest look into the evolution of space. And in the Hubble images, scientists saw a pattern. As they peered farther back in time, there were fewer and fewer galaxies, and they were smaller and smaller. This makes intuitive sense. Just like fossils in the oldest layers of the Earth's crust represent more primitive forms of life, the oldest galaxies in a deep field image ought to represent more primitive galaxies. And they differ from modern galaxies, because they had the shortest amount of time to assemble. They were like teenagers compared to the large adult galaxies of today. When James Webb went online, astronomers were eager to peer a bit more deeply into the past. They thought the pattern from the Hubble images would just continue. We thought we would maybe see a couple of more distant galaxies, but they would be very, very rare. But some things didn't go according to plan. Instead, when James Webb turned on, it was apparent that there was a lot more light back then and a lot more galaxies. As Caitlin Casey, an astronomer at University of Texas Austin, says, "We really didn't think there was much going on there." As a result, not long after James Webb came online in 2022, astronomers' jaws hit the floor. Webb's observations would, to you and me, seem like little smudgy red blobs among a field of other smudges and blobs. But in scientists' eyes, they represented a potential challenge to the story scientists have painstakingly constructed about the formative years of our universe. That is, sometime after the Big Bang, around the 12+ billion years ago, when the universe went from a dark, diffuse place full of gas to a light-filled universe populated by stars and galaxies. This is the era that laid the foundation for everything to come, including our solar system, and you and me. Scientists had some theories about what happened during this crucial period, but the arrival of James Webb put them to the test by observing regions of space humans have never seen before. And even though the galaxies appear to our eyes as smudgy blobs, scientists can study the quality of light coming from them and make inferences about their size and age. Early analyses revealed many of these galaxies were apparently huge, full-fledged adults, not teens. Put simply, we have found really mature, large, bright galaxies back even farther than we expected. And to further the fossil metaphor, it would be like finding evidence of advanced life forms in layers of the Earth when life ought to have been just starting out. In more fun terms, Casey explains it's like, at the earliest times the universe was having a party, and we had no idea it was happening. Okay, you might be thinking, so what? We got big, bright, plentiful galaxies way back near the beginning of time. Unexpected, perhaps, but it's not like it's violating the laws of physics, right? Well, the problem is time. The impossible early galaxies captured by James Webb have had very, very little time to assemble. It's kind of like if you were flipping through a family photo album and came to the realization that your grandmother grew to be an adult from an infant in just a couple of months. Such a finding might make you wonder if we're missing a big piece of understanding human development. Or somehow, the pace of human development worked differently in the past. If these galaxies contain the number of stars implied by these early observations, it should be nearly impossible for them to exist. It would require all of the gas in the system being converted into stars, which is something you never see kind of anywhere in the universe at all. So, even in the galaxies that are really intensely forming stars, we see more gas than stars. Gas is always left over in the process of forming stars out of it. Which is to say, even more simply, these James Webb observations on their face make no sense. So, what explains these bright, large galaxies? The short answer is they don't yet know. That's also why many scientists were agog that if the observations were correct, everything we know about cosmology is wrong at some level. In other words, stunning discoveries made by Webb could lead to a wholesale rewriting of the history of time. Most scientists agreed there's something big to be learned here. And it is these moments in science when observations don't match predictions that are the exciting ones. They often pave the way for fundamental new insights, and the more unexplainable, the more exciting they are. We've experienced these exciting chapters in science before. In the 1960s and 70s, when Vera Rubin observed galaxies rotating at unexpected rates, it opened the door for the discovery of dark matter, a hugely important, deeply mysterious substance that makes up 85% of all matter and acts as the scaffolding of the universe. And then an unexpected observation in the orbit of Mercury in the 19th century could only be resolved when Albert Einstein reconceptualized our understanding of gravity in the 20th century. These moments of "this can't possibly be right" often lead scientists to uncover deeper truths or reveal new, uncharted depths of their collective ignorance. But while most of astronomers believed there is indeed something odd about these galaxies, a note of caution, it is still early, and more observations need to be done to confirm their age and size. As the Christina Williams, an astronomer at NOIAR Lab, says, "We don't have enough data yet. We have to keep in mind that the amount of data James Webb has produced is actually just probing the tiniest fraction of the universe right now. We have very small areas in the sky that we've looked at. Some of the excitement around these galaxies might dim with more time, but if they are verified, scientists need to figure out why they are there." The scientists outlined a few possibilities, ranging from small tweaks to our understanding to, as Boylan Colchin, a University of Texas Austin astronomer calls them, the most disruptive options. What's so exciting is that each option is its own fork, leading to new questions, new possibilities, and new understandings of our science or the universe. Option 1. It's possible that stars and galaxies just formed differently and perhaps more efficiently earlier on in the universe. In the words of Casey, if you think about the early universe, it's a really dark place compared to where we live now. There were simply fewer stars and galaxies. And that light actually impacts how stars form out of new gas clouds. It makes it harder sometimes to form stars. In the early universe, those floodlights are not on, and so you could form stars really, really quickly, in a way that can't happen today, because right now, the floodlights are on. The idea is that starlight itself impedes the development of other stars. As Boylan Colchin says, maybe that slowing down of star formation didn't happen in the early universe, which then led to these massive galaxies. But exactly how, the scientists aren't sure. Thus, this option would be unexpected, but wouldn't require a fundamental sort of revision to everything we know about galaxy formation and cosmology. Option 2. What if it's not stars that are making these galaxies appear so bright? A key realization occurred in late 2023, that galaxies don't typically form stars continuously and at the same rate, but rather are punctuated and highlighted by brief events known as starbursts. Starbursts today typically only occur in small regions within most galaxies, creating gigantic amounts of ionized hydrogen and leading to a rapid period of star formation, where large populations of stars, including short-lived, massive, ultraviolet-emitting blue stars, all form at once. The recognition that star formation wasn't continuous early on, but rather was bursty in exactly this fashion, was extremely important. In these small, early galaxies, it was very likely that the entire galaxy itself could be undergoing a starburst, where stars formed all at once all throughout it. These episodes would dramatically, but only temporarily, increase a galaxy's brightness. Our unstated assumption that light traces mass was not necessarily true. Light can spike from transient episodes and outshine what's expected for a galaxy's given mass. These episodes of bursty star formation, accompanied by giant and supergiant stars, as well as supernovae, could definitely help explain why so many bright galaxies were seen so early on. But now, in a brand new study, scientists from the Sears team, working with some of the earliest James data, have identified a fourth contributor to these bright early galaxies. Light that's being emitted, again, not continuously, but in bursts, by their central, supermassive black holes. One of the more surprising discoveries from James Webb is that stars in a galaxy and the central, supermassive black hole within a galaxy don't exactly grow up together. Instead, it appears that the seeds of massive black holes, with masses between 10,000 and 100,000 solar masses, can form alongside or even prior to the very first stars, simply from colliding streams of cold gas. Today, the most massive black holes are huge, with tens of billions of solar masses inherent to them, about 0.1% of the stellar mass of those galaxies. But early on, black holes were still very massive, with tens of millions, hundreds of millions, or even a billion solar masses in just the first 800 million years of cosmic history. However, importantly, the galaxies that house them are much lower in mass than they are today, so that the black hole to stellar mass ratio of these galaxies isn't 0.1%, but can be 1%, 10%, or even up to 100%. These are known as overmassive black holes, and when they're active, they can shine very, very brightly. All black holes, but especially overmassive black holes, can consume gas from their surroundings, and when they do, they heat the gas up. It can get so hot that the gas doesn't just emit infrared heat light, but it can emit visible, ultraviolet, and even X-ray light. When we see a little red dot in the sky with James Webb's eyes, we're seeing the sum total of all the light produced. Light from the stars inside, plus light from any active supermassive black hole activity occurring inside. Since they only appear as a single point, it's very difficult to disentangle what light comes from what component of the galaxy. What's remarkable is that, as has been done in a new study, when you account for this black hole-produced light in these little red dots, the remaining early galaxies are right in line with what the Standard Model of Cosmology, or LCDM, predicts. But while this explanation solves some problems, it deviously opens the door to other vexing questions that could break our understanding of the universe in other ways. Their question: why the heck are there so many supermassive black holes in the early universe? Scientists know supermassive black holes played some role in galaxy development. But if these Webb observations represent black holes, it blows our estimates of how many powerful, massive, supermassive black holes at this time should exist out of the water. We do not know how the black holes got so massive so fast. Again, the essential problem here is the observations aren't matching expectations, which makes scientists think they are missing something in their understanding of the universe. Something potentially very big. Option 3. The most extreme possibility is that scientists are missing a big piece in their understanding of cosmology. Cosmology itself is a combination of science and narrative, a recipe that, when properly understood, serves as a story explaining how the universe came to be as it is today. It is a field in which scientists are constantly piecing together fragments of information from the most distant corners of space and time to build a comprehensive picture of the universe's history. At its core, cosmology is about understanding the formation of the universe from the very beginning and how all its components, stars, galaxies, and even the mysterious substances like dark matter and dark energy, came to be. One of the earliest and most valuable observations for cosmologists is the afterglow of the Big Bang. This faint radiation, which scientists have measured in various wavelengths, represents a snapshot of the universe in its infancy, long before stars had formed. The early universe, which can be observed through this afterglow, provides a starting point for understanding the sequence of events that shape the cosmos. From this image, cosmologists can tell a story about the universe's evolution, drawing on their knowledge of physical laws such as gravity and electromagnetism. This information allows them to trace how the universe transformed from a hot, dense mass into the expansive cosmos that we see today, filled with galaxies, stars, and planets. Despite the impressive strides made in cosmology, scientists themselves acknowledge that their understanding is far from complete. Much of what we see in the universe is still a mystery, particularly when it comes to the elusive concepts of dark matter and dark energy. Dark matter is an invisible form of matter that is thought to play a critical role in holding galaxies together, preventing them from flying apart due to the forces at play within them. On the other hand, dark energy is an even more mysterious force that is believed to be responsible for the accelerated expansion of the universe. Together, these components make up a significant portion of the universe, but their exact nature remains one of the most profound, unanswered questions in cosmology. However, beyond these well-known gaps in knowledge, there is the possibility that the entire narrative of cosmology may be incomplete in ways that scientists have yet to consider. This presents the most radical and potentially disruptive option in the field of cosmology. Despite the fact that the current model has been remarkably successful in explaining a wide range of phenomena, from the formation of galaxies to the large-scale structure of the universe, there could be fundamental elements missing from the picture. Boylan Colchin, an expert in cosmology, notes that it is difficult to imagine a complete overhaul of the cosmological model because of its success in so many areas. He explains that even with the many gaps in our knowledge, the current understanding of cosmology has managed to explain much of the universe's behavior and structure as we observe it. However, this success does not mean the story is fully accurate. The recent observations from the James Webb Space Telescope, for example, could challenge existing cosmological models, requiring adjustments to our understanding of the universe. The data from this powerful observatory could lead to new insights into the age of the universe, forcing scientists to reevaluate the timescale of cosmic events. Additionally, these observations could suggest that dark matter and dark energy are far more complex than previously thought, leading to a new chapter in the story of the cosmos. These potential revelations could, in turn, lead to profound shifts in our understanding of the universe's origins, structure, and future. Boylan-Kolchin's comments highlight the range of possibilities that could result from the new observations. He notes that any of the options that would address the current gaps in our cosmological model would be disruptive in some way. Whether it's altering our understanding of the universe's age, redefining the role of dark matter and dark energy, or introducing entirely new components to the picture, the implications of these changes would be far-reaching. As he states, all of those options are disruptive in some way. This brings us to the most speculative and intriguing possibility, that there may be some other component of the universe that scientists have not even considered yet, a hidden factor that could radically alter our view of the cosmos. The importance of discovering the truth behind these possibilities might not be immediately obvious to everyone. Some may ask, why does it matter if scientists figure out which option it is? After all, the universe is vast and complex, and humans are just a tiny part of it. As one might argue, the universe was not designed with the human mind in mind, and so it might be futile or even arrogant to expect that we could fully comprehend its intricacies. The universe's structure, its age, and the forces that govern it are so far beyond our everyday experience that it may seem irrelevant whether we ever uncover all of its mysteries. In this view, the pursuit of cosmology could appear as an intellectual endeavor that has little bearing on our daily lives. However, this perspective overlooks something fundamental about humanity's relationship to the cosmos. Understanding the universe is not just about grasping abstract scientific facts. It is about understanding our place within it. As Lambrides, another expert in the field, argues, if the world around us depends on what it took to get to this world, we need to study that path. This path is the history of the universe itself, and it is through tracing this history that we can begin to answer some of the deepest questions about our existence. Why is Earth here? Why did the Milky Way form the way it did? Why does our solar system exist at all? These questions are not just about our immediate environment, they are deeply connected to the very beginning of the universe. Humans, in a sense, find themselves as part of an intricate cosmic puzzle, a puzzle that stretches back billions of years to the birth of the universe itself. The more we delve into this puzzle, the more complex and mysterious it becomes. Understanding the origins of the universe is not just an intellectual exercise, it is a way of understanding who we are, where we came from, and how we fit into the grand scheme of things. Every discovery, whether it is a new observation about the early universe or a shift in our understanding of dark matter, brings us one step closer to uncovering the secrets of our existence. The exciting part of this journey is that we are not alone in this pursuit. In fact, we are currently experiencing what can be considered the golden age of astronomy. This is an unprecedented time for astronomical research and exploration, with remarkable advancements in technology that enable scientists to look deeper into the cosmos than ever before. The field of astronomy has always been driven by the search for answers, but today, this search is empowered by powerful new tools and instruments that make the once unimaginable possible. Thanks to state-of-the-art telescopes, both on the ground and in space, we are now able to observe distant galaxies, stars, and exoplanets with an unprecedented level of detail and precision. These sophisticated instruments have opened up new realms of observation, allowing us to explore the universe in ways that were previously beyond our reach. One of the most powerful of these tools is the array of modern telescopes that dot the Earth and our skies. These observatories, equipped with cutting-edge technology, are able to capture data from across the electromagnetic spectrum, from radio waves to X-rays, each wavelength revealing different aspects of the universe. For example, the Hubble Space Telescope has allowed us to peer into distant galaxies, providing us with images of the early universe as it looked billions of years ago. Meanwhile, ground-based observatories like the Very Large Telescope in Chile allow astronomers to study stars, planets, and other cosmic objects in great detail. These telescopes work together, contributing to a vast global network that continually enhances our ability to explore the universe. But it is not just telescopes that are revolutionizing our understanding of the cosmos. Advances in other fields of technology, such as computational simulations, space probes, and data analysis techniques, are helping scientists to solve some of the most enigmatic mysteries of the universe. The development of supercomputers has made it possible to run simulations of galaxy formation, black hole behavior, and the interactions of dark matter and dark energy, providing valuable insights into processes that happen on a scale far beyond human experience. In addition to computational advancements, space exploration has provided us with unprecedented data. Space probes, such as NASA's Voyager spacecraft, have been sending back valuable information from the farthest reaches of our solar system, offering a rare and profound glimpse into the distant regions of our cosmic neighborhood. These probes are instrumental in expanding our knowledge of the outer planets, moons, and even interstellar space, where few other methods of observation are possible. Furthermore, the continued launch of new space missions promises to push the boundaries of our understanding even further. These missions, equipped with cutting-edge instruments, aim to explore previously uncharted territories and gather data that could lead to groundbreaking discoveries. Whether it's studying the atmospheres of exoplanets or investigating the nature of cosmic phenomena like supernovae or gamma-ray bursts, each mission holds the potential to provide crucial information about the universe's most complex and elusive aspects. Collectively, these technological innovations are not only enhancing our ability to observe the cosmos, but are also reshaping how we perceive the vast, mysterious universe that surrounds us. The convergence of these advancements is propelling us closer to solving some of the greatest cosmic enigmas. The study of dark matter has been one of the most perplexing challenges of contemporary physics. Despite being invisible and undetectable through direct means, dark matter makes up about 27% of the universe's total mass and plays a crucial role in its structure and behavior. But in recent years, there has been significant progress in the search for dark matter. Scientists have been able to detect its effects on visible matter, such as the gravitational lensing effect it causes when light from distant stars or galaxies is bent by its gravitational pull. Additionally, research into hypothetical particles like WIMPs, also known as weakly interacting massive particles, and axions has led to a flurry of experiments designed to detect these particles directly, though they have yet to be conclusively found. Despite this, these developments mark an important step forward, and each breakthrough brings us closer to unraveling the mystery of dark matter. The continued advancements in observational technology, particle detectors, and theoretical modeling will undoubtedly lead to future discoveries that could finally reveal the true nature of dark matter. Alongside the study of dark matter, our understanding of the early universe has also undergone significant changes. For much of human history, the origins of the universe were the subject of philosophical speculation and religious teachings. It wasn't until the 20th century that scientific theories began to emerge, with the Big Bang theory becoming the dominant explanation for the universe's birth. In the decades that followed, advancements in observational astronomy began to offer ways to test these theories and refine our understanding of the cosmos. One of the most important pieces of evidence supporting the Big Bang theory came from the discovery of the CMB radiation, the faint afterglow of the Big Bang. This radiation provides a snapshot of the universe as it was just 380,000 years after its creation, offering valuable insights into the temperature, density, and composition of the early universe. The study of CMB radiation has revolutionized our understanding of the early universe, providing a direct observation of its conditions shortly after its birth. The patterns and fluctuations in the CMB help scientists learn about the fundamental forces that shaped the universe and the processes that led to the formation of galaxies and other large-scale structures. As telescopes and detectors have become more sophisticated, scientists have been able to probe the CMB with greater precision, refining models of the universe's evolution and gaining a deeper understanding of the forces that shaped it. Another area of exciting discovery is the search for exoplanets, planets that orbit stars outside our solar system. The discovery of thousands of exoplanets over the past 2 decades has been one of the most remarkable achievements in modern astronomy. These planets come in a wide variety of sizes, compositions, and orbits, but the most intriguing ones are those located in the habitable zone of their parent stars. The habitable zone is the region around a star where conditions are just right for liquid water to exist, which is considered one of the key ingredients for life as we know it. The possibility that such planets could harbor life has captivated the imagination of scientists and the public alike, prompting further research into their composition, atmospheres, and potential for supporting life. Recent advancements in space telescopes, such as NASA's Kepler and James Webb telescopes, have enabled the detection of exoplanets with greater sensitivity, leading to the discovery of potentially habitable worlds. In addition to detecting planets, these missions are allowing scientists to analyze the atmospheres of exoplanets in unprecedented detail. By studying the chemical makeup of these atmospheres, scientists hope to uncover signs of life, such as the presence of oxygen or methane, which could be indicative of biological activity. Though we have not yet found definitive proof of extraterrestrial life, the growing body of knowledge about exoplanets has brought us closer than ever to understanding the potential for life beyond Earth. In conclusion, we are living in a time of unprecedented scientific progress. The convergence of cutting-edge technology, international collaboration, and the relentless pursuit of knowledge is bringing us closer to understanding the most profound questions about the universe. As we push the boundaries of human exploration, we are uncovering the answers to cosmic enigmas that have occupied the minds of philosophers, scientists, and dreamers for millennia. The mysteries of the cosmos, once distant and unreachable, are now within our grasp, and the future of scientific discovery looks brighter than ever before.
It's so powerful, it might have just shattered our understanding of the universe.
Out in the depths of space, the James Webb Space Telescope is living up to its hype. From inexplicably bright galaxies to life on alien planets, and even the potential demise of our standard model of the universe, the most powerful telescope ever built has blown our minds with its stunning discoveries of multiple structures that shouldn't exist.
Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden we realize that we may have to rewrite all the textbooks about the beginning of the universe.
Join us as we dig deep into how the shocking discoveries of James Webb could destroy the universe. To understand the dilemma, let's start by taking a quick look at the Big Bang, our best supported theory of our universe's origin. Originally, the Big Bang was a simple idea that grew out of 3 facts, all put together. In Einstein's general theory of relativity, a universe filled with any uniform distribution of matter and/or energy will not be stable in a static configuration. The fabric of space in that universe must either contract or expand. Observationally, there are spirals and ellipticals in the sky, and they lie well beyond the Milky Way. Their distances can be measured. Also, observationally, the light from these spirals and ellipticals appears to be shifted, with more distant objects exhibiting a greater redshift in direct proportion to their distance, consistent with an expanding universe. By combining these 3 facts, we'd conclude that the universe, if it's expanding and becoming less dense today, must have been smaller and denser in the past. The first person to synthesize this information together was Georges Lemaitre, who did it in 1927, although others would independently come to the same conclusion, including Howard Robertson in 1928. Edwin Hubble in 1929, and Arthur Walker a few years later. Over time, we were able to derive many more consequences from the Big Bang, including that the early state must have been hotter as well as denser, and that as the universe expands, it also cools. This allowed us to predict that there would be a leftover bath of low-energy radiation, with a blackbody spectrum in all directions, arising from when the universe cooled through the threshold that enabled it to form neutral atoms. At even earlier times been hot and dense enough to initiate nuclear fusion reactions before any stars could form, leaving us with an initial abundance of elements other than hydrogen among the pristine set the universe begins with. And that, once neutral atoms form, the universe begins gravitating to form structure in the universe. Stars, star clusters, clouds of gas, galaxies, galaxy clusters, and eventually the great cosmic web, filled with filaments and voids. All of these aspects of the Big Bang have been verified and validated, ruling out a great many alternatives that cannot reproduce these successes. Today, there are 3 additional ingredients that we've learned, and tested and verified, are also present in the universe. Dark matter, which clumps and gravitates but doesn't collide with normal matter or photons. Dark energy, which behaves as a form of energy inherent to space itself. And cosmic inflation, which limits how far back into the past we can extrapolate the hot Big Bang before matter and radiation no longer dominated the energy contents of the universe. This picture enables us to do something remarkable. Inflation allows us to describe the initial conditions of the universe at the start of the hot Big Bang, how hot and dense it was, what the initial spectrum of density imperfections were, including that we're all adiabatic, Gaussian random fluctuations, and what the magnitude of these fluctuations were on all cosmic scales. Our knowledge of the Standard Model, plus the additions of dark matter and dark energy, enable us to state what the various types, energies, and abundances of all the different species of energy were at all cosmic times. From that starting point, our knowledge of the laws and interactions that govern the universe enables us to time-evolve these initial conditions from the start of the hot Big Bang all the way up through the present day. We can make both theoretical predictions and perform numerical simulations that tell us what should arise and when in an expanding universe that begins with a hot Big Bang and the properties we've determined it ought to have. However, despite all the observational evidence we have supporting this picture, it may not be fully correct. Each time we observe the universe in a new way, we have to check that what we're seeing is still consistent with this model. And with the recent addition of the James Webb Space Telescope to the arsenal of tools astronomers have, James Webb continues to fuel doubts about the Big Bang theory, as its early universe observations cannot be explained by current cosmological models. The James Webb has literally gone further than any similar instruments used by NASA before. As Matt Greenhouse, who has served on the James Webb's senior staff as a project scientist, the James Webb Space Telescope has given humanity its first high-definition view of the infrared universe. Thanks to Webb's unprecedented capabilities, for the first time, we're beginning to discover and characterize galaxies found in these very, very early stages of our cosmic history. Prior to James Webb, we had one confirmed galaxy, GNZ11, at an age of about 400 million years after the Big Bang, and only one other galaxy candidate, possibly at an age of around 330 million years after the Big Bang. No other stellar or galactic signals from such early epochs had ever been seen. Fast forward to the present day, more than 2 years after James Webb began science operations, and the story has changed dramatically. We have over 100 galaxy candidates from James Webb that take us back to the first 300 million years of the universe, and several of them have already been confirmed to indeed be ultra-early and ultra-distant. GNZ11 is now only the 11th most distant galaxy known. All 10 of the top 10 most distant objects were discovered and measured with James Webb. However, what's notable is that many of these early galaxies that James Webb is finding have peculiar, puzzling properties about them that appear difficult to reconcile with this theoretical picture that the universe has painted for us. For example, they appear to be very massive, very bright, very rich in heavy elements, very actively forming new stars, and very rich in gas. The fact that we see so many galaxies with these properties so early on is puzzling, because we believe we understand how gas infalls onto these early galaxies, and how star formation feeds back and prevents future gas from falling in. There's a limit for how fast material can accrete onto these objects, and although certain physical conditions can lead to an object temporarily overcoming that limit, it shouldn't be sustainable over such long timescales. Therefore, when we look at these very early galaxies, we do get the impression that something is amiss. Webb's finding then caused a stir in the astronomical world, with some scientists suggesting that it had put our current view of galaxy evolution, or even our understanding of the universe, into doubt. There weren't just inexplicably large ancient galaxies on James Webb's list of discoveries, but whopping black holes, too. The first, Sears 1019, had a mass 10 million times that of our Sun and was found by the James Webb Telescope just 570 million years after the Big Bang, making it the oldest black hole ever spotted at the time of its discovery in April 2023. We say "at the time" because James Webb didn't rest on its laurels. Earlier this year, the telescope broke its own record again for the most distant black hole ever seen to date. The black hole dwells in the ancient galaxy GNZ11, which is 13.4 billion light-years away and is thus seen as it was just 400 million years after the Big Bang. The black hole itself is around 6 million times as massive as the Sun and seems to be feeding on matter from its surrounding galaxy 5 times more rapidly than the limit suggested is sustainable by current theories. And according to scientists, this discovery could be a giant step forward for black hole science, especially in understanding how supermassive black holes reached masses equivalent to millions of billions of times that of the Sun in the very early epochs of the universe. For decades, how these gigantic space-time ruptures swelled to such staggering scales so early on is an ongoing mystery. Astrophysicists are currently exploring options that include the black holes being formed from the rapid collapse of giant gas clouds, although they haven't ruled out that some may have been seeded by hypothesized primordial black holes, thought to be created moments after, and in some theories even before, the universe began. In another stunning observation, the James Webb Space Telescope has found more thousands of Milky Way lookalikes that shouldn't exist, swarming across the early universe. Shaped like warped vinyls and sporting delicate spiral arms, the Milky Way doppelgangers were found by James Webb more than 10 billion years into the universe's past, during a period when violent galactic mergers were thought to have made an abundance of such fragile galaxies impossible. But Webb's finding revealed that the disk galaxies are 10 times more common in the early universe than astronomers previously thought. The strange discovery joins others made by James Webb that point to a deepening mystery around how large galaxies, and with them the potential for life, first bloomed in our universe. However, not stopped there, Webb's ultra-powerful eye has also revealed glimpses of completely new, unexplainable objects. After being trained on the Orion Nebula, the Webb telescope found 42 pairs of Jupiter-mass binary objects, or jumbios, Jupiter-sized planets drifting through space in pairs, some as far apart from each other as 390 times the distance between Earth and the Sun. The jumbos are too small to be stars, but as they bafflingly exist in pairs, they are unlikely to be rogue planets ejected from solar systems. Their discovery has alerted astronomers to a brand new formation mechanism for planets or even for failed stars. While James Webb glimpsed deep space unlike ever before, it caused a stir in the whole scientific community as piercing through dust to find an ancient ghost. Look at this picture. It's a very blurry, highly dust-obscured resident of the cosmos, whose name is only a string of numbers and letters. It even sits at a distance so far from Earth that it slips in and out of the watchful eyes of various telescopes. The image, captured by the powerful James Webb Space Telescope, spotlights galaxy as TECC 71. But what's striking here is that we're seeing as TECC 71 the way it was just 900 million years after the Big Bang. That's when the universe was turning on its very first stars, absolute eons before our solar system was born. The Webb's view of this galaxy as a hazy speck of light is a far cry from many other glorious images of galaxies and galaxy clusters in its repertoire. However, even this smudge holds important lessons for our understanding of the early universe. Elsewhere, James Webb has helped set yet another record. Using the James Webb Space Telescope, astronomers have discovered star clusters in the cosmic gems arc that existed just 460 million years after the Big Bang. This marks the first discovery of star clusters in an infant galaxy, seen as it was when the 13.8 billion-year-old universe was less than 500 million years old. The cosmic gems arc, initially discovered by the Hubble Space Telescope and officially designated SPT 0615JD1, is a gravitationally lensed infant galaxy around 13.3 billion light-years from Earth. That means light from this galaxy, seen by James Webb, has been traveling to Earth for around 97% of the universe's lifetime. The international team of astronomers behind this discovery found 5 young, massive star clusters in the cosmic gems arc. These clusters existed during a period when young galaxies were undergoing intense bursts of star formation and emitting huge amounts of ultraviolet light. This radiation may be responsible for triggering one of 2 major phases in the evolution of the universe, the epoch of cosmic reionization. And when pointing Webb's sights on a star cluster about 1,000 light-years from Earth, astronomers discovered some unusual objects that is likely to be the least massive, free-floating brown dwarf that has been observed to date. In another remarkable observation, James Webb spotted a massive, gassy tendril composed of 10 closely packed galaxies stretching over 3 million light-years. According to the researchers, this ancient filament of gas and stars may represent the oldest known thread of the cosmic web. Another addition to the Webb telescope's long list of cosmic distance records was its discovery of the most distant gravitationally lensed object ever seen, an Einstein ring, produced by the warping of light from a distant galaxy around a mysteriously dense foreground galaxy. How distant? A mind-bending 21 billion light-years away, which, given the universe's 13.8 billion years of age, means that the light from the galaxy traveled almost twice that distance due to the cosmos's expansion. Besides making for a very pretty picture, distantly lensed light shows like this could help astronomers to understand the puzzling nature of dark matter, the unseen substance believed to make up 70% of the universe's matter. Notably, while focusing to unlock the secrets of deep space, the James Webb Space Telescope also is revolutionizing our understanding of our closest cosmic neighbors. With its powerful infrared instruments, sharp spatial resolution, and exquisite sensitivity, Webb is forever changing our view of our celestial backyard. It is helping scientists answer important questions about our solar system, including how was the solar system formed and how has it changed over time? Where did the chemicals necessary for life on Earth, like water and carbon compounds, come from? What are the icy small bodies in the outer solar system made of? How are planets around other stars like planets in our solar system? Webb's extraordinarily sensitive spectroscopic instruments and state-of-the-art imaging capabilities enable analysis and mapping of solar system objects' atmospheres and surfaces. This is critical for studying planets, dwarf planets, moons, comets, asteroids, and ring systems. However, because Webb cannot point toward the Sun, it cannot observe objects between it and the Sun such as Mercury, Venus, Earth, or Earth's moon. Despite these challenges, exciting early results prove that it is possible to study planets with Webb. The telescope captured images and spectra of Mars, which allow scientists to study short-term phenomena like dust storms, weather patterns, seasonal changes, and, in a single observation, processes that occur at different times during a Martian day. In addition to finding the speedy Jovian jet stream described, Webb's view of Jupiter includes many fascinating details, including auroras, hazes, and tiny moons. In addition to finding carbon on the surface of Jupiter's moon Europa that likely originated in its subsurface ocean. In the newest study, astronomers have used James Webb to find previously unseen structures and activity in Jupiter's atmosphere, above the Great Red Spot. These odd features seem to be caused by powerful atmospheric gravity waves. The Great Red Spot is the largest storm in the solar system, twice as big as Earth, and is believed to have been raging for at least 300 years. The winds of the Great Red Spot rage at around 430 to 680 kilometers per hour, up to 3.5 times as fast as a tornado here on Earth. But, despite the storm's age, size, and power, scientists had actually suspected that the atmosphere of Jupiter above the Great Red Spot wasn't all that interesting. However, these new observations delivered by James Webb's NIR-SPEC instrument, which observed the massive Scarlet Storm in July 2022, show that this assumption couldn't have been more wrong. After all, Jupiter never ceases to surprise. The telescope also detected a shockingly large water vapor plume spewing from Saturn's moon Enceladus. For the first time, Webb is giving scientists a direct look at how the water gushing from the surface of Enceladus, first detected by the Cassini spacecraft, feeds the entire system of Saturn, including its rings. Using Webb's infrared vision to study the atmosphere of Saturn's moon Titan, the only moon in the solar system with a dense atmosphere, scientists detected clouds and observed airflow. For those who don't know, Titan is the only planetary body other than Earth that currently has rivers, lakes, and seas. However, unlike Earth, the liquid on Titan's surface is composed of hydrocarbons, including methane and ethane, not water. Put Titan aside, Webb's huge mirror and infrared sensitivity make it easier to see small, faint bodies such as Kuiper Belt objects, comets, asteroids, and centaurs. In the first demonstration of this capability, described in detail above, Webb captured the DART impact, NASA's inaugural attempt to move an asteroid in space. Webb enabled another long-sought scientific breakthrough, this time for solar system scientists studying the origins of Earth's abundant water. Using Webb's NIR-SPEC, or near-infrared spectrograph instrument, astronomers for the first time have confirmed gas, specifically water vapor, around a comet in the main asteroid belt. This indicates that water ice from the primordial solar system can be preserved in that region. However, the successful detection of water comes with a new puzzle. Unlike other comets, Comet 238P Reid had no detectable carbon dioxide. Scientists also used Webb to capture the shadows of starlight cast by the thin rings of Chariklo, a small icy body more than 2 billion miles beyond the orbit of Saturn. Only 250 kilometers, or 1,051 times smaller than Earth in diameter, Chariklo is the largest of the known centaur population. Its rings orbit at a distance of about 400 kilometers from its center. Information gathered from these rings will allow astronomers to explore the ring's thickness, the sizes and colors of the ring particles, and more. Scientists hope to gain insight into why this small body even has rings at all, and perhaps detect new, fainter rings. Besides, remember that many different kinds of ice exist in the outer solar system, not just the familiar water ice. Other molecules besides water can form ices, such as nitrogen, methane, ammonia, and carbon dioxide. Webb excels in the study of ices in the solar system through the use of spectroscopy. Most often, It provides reflectance spectra, sunlight shining on an object and reflecting back, while the surface absorbs particular wavelengths of light. For ices in the outer solar system, it's not just the composition that matters, it's also the shape and structure. Different structures of ice, such as amorphous, crystalline, and irradiated, look different in spectra. The type can tell scientists about the temperature history of the object. In crystalline ice, the molecules are arranged in a highly regular pattern, forming lattices, such as in typical water ice on Earth. With amorphous ice, the molecules are irregularly grouped. In the cold, primordial gas between stars and across the universe, amorphous ice is the most common form. This is why Webb's integral field units are especially important. With a spectrum in every pixel, scientists can map out the surface of an object. One good example is Jupiter's moon Europa. By looking at a map of the carbon dioxide on Europa, we can tell that the carbon originated in the oceans because it is most abundant in a region where the terrain is quite new. Another example of the exquisite quality of Webb spectroscopy is the clear signature of crystalline ice revealed for the first time on Chariklo. Ground-based telescopes had hinted at this ice, but Webb saw the crystalline ice signature for the first time. Some of Webb's most intriguing discoveries involve searching for the building blocks of life beyond Earth. This search hinges on the accurate identification of chemical markers, such as water, carbon dioxide, and ammonia. These markers have strong infrared signatures that Webb can detect in the atmospheres and on the surfaces of planets, moons, and smaller bodies. And in a remarkable finding, James Webb has spotted the potential signs of life in alien farts on a Goldilocks water world 120 light-years away. The exoplanet it found, K2-18b, is a sub-Neptune planet, weighing in somewhere between the mass of Earth and Neptune, orbiting the habitable zone of a red dwarf star. After taking an atmospheric spectrum, the Supreme Space Observatory found it rich with hydrogen, methane, and carbon dioxide, all chemical markers of a hydrogen-rich Hycean world that is a prime contender for extraterrestrial life. More tantalizing still was the detection of dimethyl sulfide, a cabbage-smelling compound only known to be produced by microscopic algae in Earth's oceans. The researchers want to take more peeks at K2-18b and worlds like it to find further evidence for extraterrestrial life beyond our planet. Fascinatingly, the latest result of James Webb suggests an exoplanet is our best bet at finding an alien ocean. Dubbed LHS 1140b, the exoplanet orbits a red dwarf star about a fifth the size of the Sun and sits 48 light-years away from Earth in the constellation Cetus, which, as luck would have it, translates to the whale. But the most important about LHS 1140b is the fact that it lives in its star's habitable zone, otherwise known as its Goldilocks zone. As that nickname would suggest, this is the area around a star where it's neither too hot nor too cold for a world to host liquid water, but rather fits the standard by which the fairy tale character Goldilocks lives. There's also a second major win for the world. Though it has been making headlines now due to the new study involving Webb's data, LHS 1140b has actually been on planetary hunters' radars for some time. In fact, experts had already theorized that this could be a water world in the past, and even shared similar sentiments about how it could offer humanity the first ever direct evidence of exoplanetary liquid water. None of that is new. Scientists themselves have touted the world's promise previously, and an army of telescopes has investigated it in solid detail, including the now-retired Spitzer telescope, the Hubble Space Telescope, and the Transiting Exoplanet Survey Satellite, or TESS for short. However, there was something missing until now: the James Webb Space Telescope's keen eye. It was necessary because, for a long time, there was something like a gap in the literature about LHS 1140b. Basically, the trouble was that scientists couldn't quite confirm whether the exoplanet is a mini Neptune, a planet less massive than our original Neptune, but one that still has Neptunian characteristics. Or a super-Earth. A super-Earth is a world that's larger than Earth, but still either rocky or water-rich. The latter typically sounds the potential habitability alarm, and James Webb, scientists had imagined, could be the one to set it off. This appears to have been an accurate inference. As the team's statement on the study suggests, their work not only strongly excluded the mini-Neptune scenario, but also confirmed the world may have a nitrogen-laced atmosphere like Earth does. It is certainly worth noting that LHS 1140b isn't exactly fully alone in its exhilarating characteristics. There are also a variety of other habitable zone exoplanets scientists are drawn to. The most obvious are probably the 7 worlds of the TRAPPIST-1 system, a planetary lineup that looks almost disturbingly similar to our solar system structure. The septet of orbs resembles our octet, and some of them are in the habitable zone like Earth is. However, a very interesting Webb study actually complicated the search for habitability in TRAPPIST-1 quite recently. It revealed that the system's anchor star is incredibly active in such a way that it could skew our observations, making us believe a world in the system is habitable when it really isn't. Even James Webb has its limitations. So, to that end, LHS 1140b does have a few special embellishments. For example, data obtained by James Webb further suggests the exoplanet's mass might be made of between 10% and 20% liquid water. And it paints a fantastical picture of what the planet might look like in simple terms. It could look like a snowball, essentially, that orbits its star while rotating in such a way that one side always faces that star. It's kind of like the moon's orbit around Earth. We can't ever see the far side of the moon because the moon rotates at the same rate it revolves around Earth. One side never faces us, and the other always does. Similarly, this would mean that if James Webb's illustration of the LHS 1140b scene is correct, the side of the planet always facing its sun would be exposed to lots of heat. This would be the part of the snowball that's melted into a liquid ocean. And yes, if so, LHS 1140b has an Earth-like atmosphere, and its surface temperature of the ocean may very well even be a comfortable 20 degrees Celsius. And that is a very promising start. A previous study, the Webb telescope, revealed details of the mysterious gas giant exoplanet WASP-39b, which orbits a star about 700 light-years away from Earth. WASP-39b is tidally locked to that star, which means the same side of the planet always faces its star. In other words, half of the planet experiences perpetual day, and the other experiences perpetual night. But the dividing line isn't black and white. There's a proverbial gray area between the two halves that experience the equivalent of eternal dawn and eternal twilight. And it's in these areas that James Webb is revealing new information. Using those data, astronomers determined the temperature difference between these two transitional areas of the planet, a whopping 200 degrees Celsius. The morning is cooler at 600 degrees Celsius, while the evening is warmer at 800 degrees Celsius. What's more, models based on Webb's data also revealed weather patterns in these regions. For one thing, the dawn side is cloudier than the evening side. For another, the prevailing winds on WASP-39b appear to move from the night side to the morning, to the day side, then to the evening, at speeds up to thousands of miles per hour. Astronomers will continue to dive into this data set to learn more about WASP-39b and other exoplanets. In addition, James Webb has mostly revealed insight into how everything began, but what about our eventual demise? Fear not, or maybe fear away, doom mongers. The James Webb Telescope had you covered this year with a spectacular light show from a dying star, a preview into the demise of our solar system. The donut-shaped ring nebula, also known as Messier 57 or M57, is a 2,200 light-years distant corpse of an exploded star, harboring at its center a tiny pinprick of a white dwarf that is the last remaining piece of the star's core. As it reached the end of its life, the star exploded outwards, hurling its innards far and wide to form what looks like a gigantic eye. The explosion likely obliterated or ejected any unfortunate planets in its way, a fate that will similarly befall our own solar system in 5 billion years' time. One of Webb's recent observations has found evidence of two giant asteroids slamming into each other in a nearby star system. The colossal collision ejected 100,000 times more dust than the impact that killed the dinosaurs. The violent impact occurred recently in Beta Pictoris, a star system located 63 light-years away in the constellation Pictoris. While the young star system currently contains at least 2 gas giant planets, it has no known rocky worlds like our own. But rocky inner planets may be in the process of forming thanks to large dust-producing collisions like the one spotted by James Webb. The researchers behind the new findings said in a presentation at the 244th meeting of the American Astronomical Society in Madison, Wisconsin. Because it is still very young, the star system's circumstellar debris disk, the vast ring of gas and dust surrounding the star, is a significantly more violent place than our own, making it the perfect place for astronomers to study the tumultuous early years of planet-forming systems. The team added that their findings could offer a rare insight into the history of our own solar system. And when it comes to hunting for the explosive deaths of massive stars in the early universe, James Webb is quite the cosmic detective. This celestial Sherlock Holmes has found evidence of 80 new early supernovas in a patch of sky as wide as a grain of rice held at arm's length. Not only is this 10 times more supernovas than have been uncovered before in such early cosmic history, but the sample also includes the earliest and furthest supernova ever seen. It's one that exploded when the 13.8 billion-year-old universe was just 1.8 billion years old. Data from the James Webb Space Telescope Advanced Deep Extragalactic Survey, or JADES program, helped a team of scientists find this unprecedented clutch of supernovas, which further includes Type 1a blasts that astronomers call standard candles and can use to measure cosmic distances. Prior to James Webb's commencing operations in the summer of 2022, only a handful of supernovas had been found dating back to when the universe was only 3.3 billion years old, equal to around 25% its current age. However, the JADES sample contains many supernovas that exploded even further back in the past. In fact, some erupted when the universe was less than 2 billion years old. On the other hand, it is worth noting that while the James Webb's primary goal is to produce awesome science, and not just pretty pictures, sometimes the pretty pictures are the awesome science. Case in point, the stunning portrait of NGC 5068, a spiral galaxy sitting about 17 million light-years away. No ordinary galaxy, this one is spouting off new stars at a record pace. A team of astronomers was able to use multiple instruments on board the telescope to capture the galaxy in all its glory. After all, James Webb has beat all our expectations. What's more, the telescope is just taking its first steps into its journey to conquer the universe. Space engineers have calculated Webb's expected 10-year lifetime could be doubled. In many ways, that is very good news. We will be able to do a lot more science with it now. In the next years, the telescope promises to deliver images of staggering beauty, while also providing scientists with data that has revolutionized our understanding of the cosmos. And that's really worth waiting. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, Thanks for watching, and we will see you next time.